So how does the operating system actually guarantees that these operations, signal and wait are atomic? Remember that many different processes may invoke wait and signal operations simultaneously. So if two processes are allowed to update the semaphore value at the same time, the semaphore could become inconsistent. The solution depends on the hardware. On a single processor system, the operating system can simply disable interrupts while executing this short critical section. Why does that work? Because if interrupts are disabled, the currently running process cannot be preempted, so no other process can enter the semaphore code until the update is complete. However, on a multiprocessor system, disabling interrupts on one CPU does not stop another CPU from executing the same code. Therefore, modern operating systems typically protect these short critical sections using spin locks. Since these critical sections are extremely short, using a spin lock here is efficient. Here we see how the wait function can be protected using a spin lock. Before modifying the semaphore, the kernel first enters the lock's entry section. It repeatedly executes test and set until it successfully acquires the spin lock. Once the lock has been acquired, no other processor can execute this critical section at the same time. Now it is safe to decrement the semaphore value and, if necessary, insert the process into the waiting queue. Immediately afterward, the kernel releases the spin lock by resetting the lock variable. Notice something interesting happens here. The potentially expensive operation, blocking the process, is not performed while holding the spin lock. Instead, the spin lock is released first, and only then does the kernel perform the context switch. This minimizes the amount of time that other processors must wait to access the semaphore. The implementation of Signal follows exactly the same philosophy. First, the kernel acquires the spin lock to ensure exclusive access to the semaphore data structure. It then increments the semaphore. If there are waiting processes, one process is removed from the waiting queue. At this point, the semaphore data structure has already been updated correctly. Therefore, the kernel immediately releases the spin lock. Only after releasing the lock does it actually wake up the waiting process. Again, this design keeps the protected critical section as short as possible. The general rule is simple. Hold the spin lock only while accessing shared kernel data and release it before performing slower operations such as scheduling or context switching. Although semaphores are powerful synchronization tools, they are also easy to misuse. Two common programming mistakes can lead to serious problems. The first mistake is violating mutual exclusion. If a programmer forgets to execute wait or place it in the wrong location, multiple processes may enter the critical section simultaneously, causing race condition and data corruption. The second mistake is even more subtle. Suppose a programmer forgets to call signal after leaving the critical section. In that case, every other process waiting for that semaphore remains blocked forever. This is something called permanent blocking, and in practice, it often appears as a deadlock or an application that simply stops making progress. Notice that these errors are usually not caused by the operating system, they are programming mistakes. That's why synchronization code must be written very carefully. A single missing wait or a single statement can completely change a single missing wait or signal statement can completely change the behavior of a concurrent program and produce bugs that are often very difficult to debug.